Good morning. My name is Liwen from National Institute for Material Science in Japan, and today I would like to share the research activity in our group on the photoelectricity energy conversion devices based on III-V Nitride Semiconductor. The III-V Nitride Semiconductor include gallium nitride, indium nitride, aluminum nitride, and their quaternary and ternary alloys. They has a very wide direct band gaps from the deep UV region to infrared region. For example, aluminum nitride has an energy band gap at 6.2 electrovolts, and indium nitride has the energy band gap at 0.7 electrovolts. So it almost covers all the spectra, which is much superior than the other material system. And in addition, this material has superior physical and chemical properties, so they can be utilized in a lot of different applications. For example, they can be used for the full-color LED displays, laser diode, which for the optical application, and also for the photodiode or photo detection. The aluminum gallium nitride is a very good candidate for the solar blend detection because they have the absorption lower than 280 nanometer. And indium gallium nitride is a very good photo detector for the visible blend detection. And another important application is the solar cell. So you can see for the indium gallium nitride, the energy band gap nearly has a perfect match to the solar spectrum. So compared to other material system which is utilized for the solar cell, theoretically indium gallium nitride can achieve a very high conversion efficiency if we take the full advantage of the InGaN material. And another very important application using the nitride semiconductor is the electronic devices. For example, the argon-GaN HAMD device has already been utilized in many fields. For example, like the RF power application for the power devices, and also in the communication devices, which is also very famous for the 5G application. And here, I will introduce all the research activities in my research group using the III-V nitride semiconductor. At first, I will introduce the material indium gallium nitride for the energy devices. So this figure shows the comparison of the InGaN material to the silicon or gallium arsenide or silicon carbide material. And compared to the silicon and silicon carbide, InGaN is the direct bandgap material, so they can have a high quantum efficiency, and the energy bandgap is higher than the silicon, so they can have a high breakdown voltage. And also the electron mobility of the InGaN material is also very good. So if we use the InGaN as the UVA visible blind photo detection, it is very promising for the flame detection because they can have a very good physical and chemical stability, especially for the high temperature detection, and I will show later. And also, as I introduced, InGaN has the perfect match to the solar spectrum, which is much better than other material system. And then I will show our result of the InGaN solar cell for the solar cell application. For both the visible blind photo detector or solar cell, to improve the quantum efficiency, it is very necessary to obtain enough the light absorption. So this requires the indium gallium nitride film has a very thick thickness, for example, around several hundred nanometer. And here we use the metal organic chemical vapor deposition for the growth of the indium gallium nitride material. And this is our material system, and the device condition is like this. And to improve the interface morphology between the indium gallium nitride and the gallium nitride, we introduced a very special long-time nitrogen polishing method to improve the interface morphology. And another modification is our MOCVD system has high pressure condition grows, because at the high pressure condition we can obtain the very good quality indium gallium nitride film at the relatively higher growth temperature. And this is our special designed high pressure MOCVD, and which can theoretically can go up to 3 atoms, so which is unique compared to other MOCVD system. And here is the indium gallium nitride obtained using our MOCVD, and we can see from the surface morphology we can observe the very good atomic steps which indicate the ultraflight surface morphology. And this is the XRD rocking curve showing the quality of the indium gallium nitride material. We can see the forwards at half maximum value for the INGAN 002 plane from XRD is only 99 arcsecond. So this is the lowest value ever reported for the indium gallium nitride. And for the 101 plane, the FWHM value is also very good. So to fabricate the UVA photo detector, and we introduced the calcium fluoride to fabricate the MRS mistype photo detector. Compared to the silicon oxide or silicon nitride insulator, calcium fluoride has a super wide bandgap energy and a large carrier effective mass. So this means we can only use the around 8 nanometer calcium fluoride can reduce the leakage current, which is much better than silicon oxide or silicon nitride, which required more than 20 nanometer thickness. And for the device, we can see that by using this calcium fluoride, the leakage current is reduced by more than 6 orders of magnitude. And also the device shows a very good spectral selectivity. The ratio between the UV light to the visible light is more than 10 to 6, so which is also the highest value ever reported, also compared to other UVA photodiode. And we also found that the device shows a very good high temperature stability, and this is the thermal stability of the dark current, and it shows the a little increase with the temperature increasing, but still is very low, lower than 10 to -6 when the temperature is higher than 500 Kelvin. And the signal to noise ratio is also very good at high temperature. And the spectral selectivity also did not degrade when the temperature is increasing. The response speed is also very good, and without the PPC observed even at the temperature higher than 463 Kelvin. So next I will introduce our work on the solar cell using indium gallium nitride. And the typical structure for the semiconductor solar cell is like this. Typically a p-n junction is utilized, and then the active region is inserted between the p-n junction to fabricate this solar cell. And in our work, now we can achieve the conversion efficiency around 1.8%. And for the other group, the conversion efficiency is still lower than 2%. So this is because the absorption region of the INGAN solar cell is still focused on the shorter wavelengths, and this is the longest wavelength absorption for the INGAN solar cell. We can see that compared to the solar spectrum, it is still cannot go to the highest absorption in the sunlight. So to obtain or to improve the conversion efficiency of the INGAN solar cell, it is very necessary to enlarge the absorption band. So this required the enriched indium gallium nitride, which has indium composition at around 40%. But this is also leads to a lot of difficulty, as I introduced before. So how to extend the absorption spectra without increasing the indium composition? And here we propose the concept of the intermediate band transition in the solar cells. So typically the solar cell has the p-n junction structure, they has the two energy level absorption from only the valence band to the conduction band. However, if we introduce another band which is inside the band gap, and the absorption can be realized from both the valence band to the intermediate band and the intermediate band to the conduction band, and combined to the band gap absorption, we can observe the band gap absorption and sub-band gap absorption, and then extend the absorption spectrum. So theoretically, if we introduce the multiple intermediate band inside the band gap, we can extend the band gap, the absorption spectrum to a very wide absorption region. And because the III-V nitride semiconductor, if we use the gallium nitride p-n junction, we have a very large band gap of 3.2 electrovolts. And in this large band gap, theoretically, we can introduce a lot of intermediate band transition. So from this point, III-V nitride is the best choice for the intermediate band solar cell. So our strategy and our structure is like this, and we introduced a multiple indium gallium nitride quantum dots embedded in the quantum well structure as the absorption region, and this is inserted between the gallium nitride p-n junction to achieve the intermediate band transition. So the multiple intermediate band is achieved by changing the indium composition in the quantum dots, and this is achieved by a stream modulation method. And here is the IV characteristic under the solo simulator illumination. We can see that by using this structure, the short circuit current density can be greatly enhanced. And this is the photocurrent spectrum, and this is the external quantum efficiency at different wavelengths. And we can see that compared to the reference solar cell, which is only using the conventional structure, our intermediate band solar cell, the absorption at the longer wavelength region is greatly enhanced, and this is because of the introduction of the intermediate band. And now the absorption region can cover from the deep UV region to as long as the 700 nanometer. So this is the longest one ever reported compared to other InGaN solar cells. And this figure shows the multiband photocurrent. So here we can see that if we use the two beam light illumination, the red light and the blue light, the photocurrent is the sum of each light photocurrent. So this is also confirmed the existence of the multi-band photocurrent. Another very important application for the gallium nitride is the electronic device. So the figure shows the on resistance and breakdown voltage for different materials. We can see that the gallium nitride, especially aluminum nitride, has a very high breakdown voltage, simultaneously a low on resistance. So this is very promising for the power device, power switching application. So this expression is from the Professor Amano, who won the Nobel Prize in 2014, and is that by using the gallium nitride power device, the switching loss can be greatly reduced compared to silicon or silicon carbide. And the gallium nitride has the up to 10 times higher breakdown voltage than silicon, and a very small size, around 1000 smaller, and very high speed because they can achieve the two-dimensional electron gas at the heterojunction, and a very high heat resistance. So it is very promising to replace the current silicon or silicon carbide for the power device application. Our group fabricated the first InGaN p-channel FETs, and this p-channel FET will utilize the InGaN heterojunction, and this device shows a very good rectifier ratio of more than 3 orders, and shows a very good FET performance. So the good performance of the p-channel FET is from the realization of the two-dimensional Hall gas at the yin-gang-gang heterojunction. The nitride semiconductor has a very unique polarization field. The spontaneous polarization and the piezoelectric polarization can generate the two-dimensional electron or two-dimensional Hall gas at the heterojunction. But the two-dimensional electron gas is already utilized for the HAMD device application. The two-dimensional Hall gas is very difficult to obtain. And here we use the yin-gang-gang heterojunction and successfully realized this two-dimensional Hall gas from the band bending. And from this is from the CV characteristic, and we estimate the carrier concentration dependent on the depth. And clearly we observed the Hall accumulation at the yin-gang-gang heterojunction. And also from the temperature dependent Hall effect measurement, we also confirmed the existence of the two-dimensional Hall gas. So the achievement of the two-dimensional Hall gas to fabricate the p-channel FET using the yin-gang-gang heterojunction is very promising, because this device cannot only work at room temperature. At the extremely low temperature, like 8 Kelvin, the device is also working very well. This is because the benefit by using the two-dimensional Hall gas is it is not dependent on the temperature. The two-dimensional Hall gas is quite different from the dopant doping, for example, using the magnesium dopant to achieve the p-type, and it has the thermal ionization energy, and it is quite dependent on the temperature. At low temperatures, the magnesium will be freeze out, but by using the two-dimensional Hall gas to achieve the p-channel FET, the device cannot be freeze out, and this is very promising for the harsh condition applications. With the development of electronic devices, the III-V nitride has attracted more and more attentions, and we also notice that it can be a promising material also for the MEMS device. From the comparison with the other material system, they have a very good piezoelectric property, a very high frequency, and also stability in the harsh condition, and also the thermal stability and chemical stability. Especially the development of the gallium nitride on silicon technology become commercialized. So this made the future integration with the CMOS technology possible. So gallium nitride will be a promising choice for the MEMS timing devices. So here we used the gallium nitride on silicon technology to fabricate the MEMS resonator. The resonator has a double-claimed beam bridge structure, and by release the silicon substrate, then we can obtain the MEMS device. And the performance of the MEMS is improved by controlling or modulating the tensile strain in the gallium nitride. And we find that the strain can dilute the energy dissipation in the resonator, and then greatly enhance the quality factor of the resonator. And the highest one we can achieve to be more than 10 to 5. So this value is also the highest one ever reported for the gallium nitride MEMS, and it's much higher for the gallium nitride or HAMD resonators. And another very good performance is the temperature coefficient of frequency, and this value can be controlled very low by also controlling the strain in the gallium nitride. And also this is also can be controlled to be lower than the silicon device. So in this presentation, I mainly introduced the research activity in our group, and we not only working on the optical devices, but also working on the electronic or the mechanical devices. For the optical devices, by using the InGaN, we fabricate the UVA photodetector, very good performance, and also we propose a new concept to enhance the performance of the solar cell, which is the intermediate band solar cell. And we fabricated the first p-channel yin-gang-gang MOS FET using the two-dimensional Hall gas which can working at the very low temperatures. And for the MEMS device, recently we achieved a very good high quality factor and a very good temperature, the frequency performance, which is also very promising for the timing device application. So finally, I will show my acknowledgement to my colleague, the postdoc researchers in my group. They contribute a lot to the research activity in my group, and the students also, they are also very helpful, and my collaborators in NIMS or outside NIMS. So thank you very much for your attention.